yourself I'm going to give to the entire gathering, which is there today for this masterclass. And it is my honor to welcome you, sir. And the discussion that I had with you over the phone was simply great. And I know that you have agreed for this particular workshop immediately without any hesitation also. So I'm very happy about it, and I thank you for that once again. And to the entire gathering for this particular workshop, I would like to introduce Michael P. Barnett, sir, for this workshop of ours as a masterclass series. And this is the first one. To give a brief introduction about him, is that he is emeritus professor of psychology at the University of South Florida, number one, number two, USA, and he is member of the editorial board of Research Synthesis Methods. And I'm very happy that yes, for this particular workshop, the first one, I have you as the first person, sir.
Thank you.
So I really appreciate it about it also. Side by side, to give another introduction about you is that I have seen that you are on the editorial board of Research Synthesis Methods, then Human Performance. These are the journals, Journal of Applied Psychology, Organizational Research Methods. And he has published many articles in the scholarly journals with respect to how to conduct research. So, sir, I'm very happy again to see you out here, including articles about research methods of meta-analysis. Now, that is the topic of our discussion also today, and I'm very happy that yes, he is going to showcase how to conduct meta-analysis using R studios. Now, we all know what is the importance of R studios as a platform. And sir, I'm giving the entire floor to you right now. And maybe you can take up from here. And I really thank you once again for joining us this evening, sir. Thank you. And I really thank all the participants and the other individuals across the countries who have joined us for this masterclass. Thanks a lot, sir. Now the floor is all yours, sir.
Thank you so much. It's an honor to be here. I really appreciate being invited to present to you. I'm really gratified that there's an international audience for this presentation. So let me just begin by see, slideshow, play from the start. Can you see the PowerPoint presentation?
Yes, sir.
Okay. For the participants in the class, for all the students and other faculty, I won't be able to see if you have a question. So if you feel free, please, to interrupt me and ask a question or make a comment. If it gets to be too much, and we're going to run out of time, then I may ask you to stop. But otherwise, feel free to just unmute and then ask away, and I'll try to address issues that you have. I'm going to, at the end of my presentation, I'm going to run through RStudio's version of the code that I used to develop this stuff. But most of the time, I'm going to be talking about what it means. So this is about meta-analysis with Metafor, and I'm planning for about 2 hours for a presentation. I'm thinking to take a break maybe halfway through, so in about an hour. Do you guys ordinarily do that? You usually take a break at some point?
Yes, sir. We can, with your approval and permission, after 1 hour, we can go ahead and we can take 5 minutes break. So
perfect. Okay. Perfect. Okay. So here we go. So I'm going to begin by saying, here's meta-analysis. And to me, meta-analysis is a summary of the quantitative results of empirical studies. So it's the data analytic part of a systematic review. when you go to the literature to research a topic, you might be interested in the effects of certain kind of leadership, for example. Then you would go and find lots of articles, and the empirical articles will have summaries in them. And if you extract those summaries and attempt to synthesize them or summarize them, the data analytic part of that is meta-analysis. So meta-analysis can be used like any other statistical technique, so to test a theory or to test a moderator or some other purpose rather than a literature summary. The data for meta-analysis is called an effect size, and that's a quantitative association of an independent variable and a dependent variable. In management, the common effect sizes are the standardized mean difference, that's the little d, and the correlation coefficient, that's the little r. If I move my cursor and I point at the d, can you see that the cursor is pointing at the d?
Yes, sir.
Okay, so I'll use that occasionally to sort of emphasize something. When we do the analysis, we use a statistical model to represent the data, so an equation that relates the dependent variable to one or more independent variables. And that's what we do when we do the data analysis. So when we do a meta-analysis, we go to the literature, we get all these effect sizes, and they're sort of an empirical sampling distribution. So you do the study, I do the study, he does a study, she does a study, we collect all the studies together. We've got a distribution of effect sizes. Our interest will be in the mean of that distribution, the variance of that distribution, and understanding and explaining for the variance in that excuse me, distribution. Our common objectives, so this is what I'm going to run through today to show and interpret the distribution of effect sizes. Find the mean of that distribution, find the variance of that distribution, explain the variance. So why are those things not all the same? And then look for problems in the data. So are we likely to see bias, outliers? Does the result change if we make different decisions, or is it robust and stays the same no matter what? The main steps, you have to go to the literature and find your studies, find your effect sizes. You have to code them, and sometimes you have to convert them from one metric to another. You have to code study characteristics, excuse me. Then we're going to calculate the distribution of effect sizes. So that's your garden variety meta-analysis. We're going to examine moderators, do some sensitivity analysis. So does it look like there's bias? And if so, can we do something about it? And then we're going to draw conclusions about our meta-analysis. And then as academic, you would share by publishing or presenting at a conference or something like that. The ones that I've highlighted are the ones that I'm going to concentrate on this evening. Okay, so the effect sizes are the data that we use to run the meta-analysis, and the correlation coefficient is commonly this little r, and its definition looks like this. You multiply the z-scores together for the x and the y, the independent and dependent variables. You add all those together, you divide by how many you got. The variance, sampling variance of this r is approximately 1 minus r squared quantity squared over n minus 1. So this is a formula that gives us an indication of how much the study would vary, the results, the correlation would vary if we did the study over and over again. So if we could get different samples, independent samples, and ran them over and over again, we'd expect to get a mean that would be roughly equivalent to this value and a variance of that distribution that would be roughly equivalent to this. In theory, this r should be rho, which would be the parameter, but we substitute r because we don't know rho when we run a study. Statisticians, because the sampling distribution of the correlation coefficient is awkward, statisticians convert from R to a statistic called Z by taking half the natural log of 1 plus R over 1 minus R. So this is called Fisher's R to Z transformation. And the sampling variance of that thing, of Z, is 1 over the n minus 3, where n is the number of people in the sample. So statisticians really like this because the parameter is now excluded, whereas here, the thing that you want to know about is in the formula. So we tend to prefer this one. So there's one of the two effect sizes that's common in marketing and management in management departments. The other one that's common is called D, and that's the standardized mean difference. And what you do to get that is you have group 1 and group 2. You have a mean for group 1. You have a mean for group 2. You find the difference, so you subtract one from the other. And you divide that by the standard deviation that's pooled within groups. So here's the formula. And basically this says this item is really the average of the standard deviations within the two groups. I mean, that's not exactly true, but this is exactly true. But you know, speaking in English, it's sort of the average of the two groups' standard deviations. The sampling variance for this statistic D is this ugly formula here. So here again, this really would be delta, the population value, but we don't know that, so we substitute D as our estimate. And so we're going to be using D and the variance, sampling variance of D in our analysis, or we'll use Z and the sampling variance of Z in our data analysis. Okay, so those are the background things that we've got to know before we go actually do the data analysis. I'm going to be presenting a meta-analysis in R. I like R. This is what I use for my meta-analyses. R is free. It's basically an online wiki so that everybody can contribute to the library of analytic functions of the programs, of the packages. It's sort of self-correcting. When people see problems, they write to the author and the author can fix it. R is fairly easy to use. There's a learning curve like most everything. It's not as easy to use as some of the programs that look like Excel, where you just put the numbers in the box. This actually does have some, command lines, some syntax to it. But what's good about that, so that's the downside, is that you have to learn the syntax. But the upside is once you've got the syntax in a file, if you change your data, you can just push the run button and the whole thing will run again. Whereas the ones with the nicer graphic user interface, you've got to go through the menus and the menus and the menus and rerun this and change that and do all these things if you change anything. So R is good for replication. You can share your file, which which I have for today's data analysis. And once you share the file, anybody can run it. The Metafor package is also the one I use. It's the one that the statisticians like. There's lots of different algorithms. There's lots of good publication quality graphs, and it's got really good diagnostics. Because you're from management, most of you, I'm not going to use this today, but I'm going to bring it up. So there's a package called PsychMeta, and that's good for the Schmidt-Hunter version of meta-analysis. And if you're publishing in a management journal, the reviewers might make you use the Schmidt-Hunter version of meta-analysis. And in that case, I recommend the PsychMeta package. It will do all the things that they want you to do. All right, so now, those are the preliminaries. So I'm gonna walk through meta-analysis using an example or an illustration of a data set. from the Pygmalion studies. So the citation is McNatt, Ancient Pygmalion Joins Contemporary Management, a meta-analysis of the result. It's from Journal of Applied Psychology in 2000. So there's the site. So what you do in a Pygmalion study is in a school, you would tell the teacher that some of their pupils are that they're getting new this year are expected to be bloomers, and they should expect to see good things from them this year, and they based on some kind of bloomer test. Or the supervisor who's just taking over a new class of recruits or a new bunch of new hires will be told that certain of these people are expected to do really well after they're trained. And the people that they're told are going to be great are actually pulled at random. So it's a nasty trick, but they're fooled sort of into believing that these people are going to be great. And so now the point of the study is to figure out, well, does this actually have an effect or not? And does it work under every circumstance, or is it just, sort of nonsense? You would think that once people got to see the actual work of somebody, they would go, no, they're just average like everybody else. On the other hand, if there's this sort of self-fulfilling prophecy where people are told this person's going to be great, and they somehow treat them in such a way as to, change how they work, then they actually will do better. So we have a series of experiments where people have done this kind of study in industry, and some people were told, these people are going to be great, and other folks not so much. And then they compared the results from the two groups, the Pygmalion group and the normal group. And the difference is expressed in the effect size D, the standardized mean difference. So that's the difference in group means divided by the pooled within group standard deviation. So that's the studies that we're going to be looking at this evening. Here's the McNatt data. So we have 17 studies from Crawford down to Frucht. And you can see there's the authors there under study, and then the year of publication. And then we've got N1 and N2, which are the number of people in the two groups. So N1 is the Pygmalion group, or the experimental group. N2 is the control group. These are the ordinary people. D is the effect size. So you can see in study 1, a guy named Crawford did the study, and the effect size was 1.15, which means that the Pygmalion group, on average, outperformed the control group by about a standard deviation, a little more than a standard deviation. And in behavioral science, that's a really big difference. Anything bigger than about a quarter of a standard deviation is pretty good size. Under org, we have M and C, and that stands for military and civilian. So some of these studies were carried out by the military, and some were done in civilian organizations. So the first one, Crawford, was done by a military study, and V there stands for the sampling variance. So I showed you, I'm going to go backwards. Here is the variance that V sub D, I computed that by N1 and N2 and D squared. Okay, that gives me the variance. Okay, let me pause here. Anybody have a question about the data or anything I've said so far?
Sir, you want them to unmute themselves and ask you a question? Or
Yes.
do you think that we should collect the questions and answer them later on? How do you say?
What is your preference? I'm fine with stopping and asking questions now if they have them.
Okay.
If you think that's going to be a problem, then we can.
I can see that there are one question which has come up from one of the participants, and he's asking Don't we take significance of the difference, that is p-value?
Do we need the significance of the difference? Is that the question?
No, the question is, don't we take significance of the difference, and that is p-value?
In these studies, the 17 studies, the authors will have done that. So the p-value for the significance was computed in each of the 17 raw studies. In meta-analysis, we don't use the combined p-value. It is possible to do that, but for reasons that I'm not going to get into, it turns out to be better to use the effect size rather than the probability. So the probability is going to depend on the sample size. So this D of 1.15, if I had 2 people here and 2 people here, it would not be significant. But if I had 180 here and 180, it would be highly significant. But either way, the size of the effect would be the same. So we will get to the p-value for significance for the combined effect across all of the studies. But the individual study p-values we're going to ignore.
Right, sir. So one more question has come in, and they're asking us now, what if the effect size is high, but the difference is not significant?
Yeah. So that's really, that is sort of one of the main reasons why we do a meta-analysis is so any given study, you can have a big effect size and not significant, or you can have a small effect size and it be significant just because the sample sizes are large or small. What we're going to do is take the effect sizes across all of these different studies and combine them to get an overall estimate of the effect. And when we do that, we're going to have good power. That is, we're going to find, if there's an effect, we should be able to see it with some reasonable number of studies. Here we've got 17. That's, when you look at all the people, by the time we combine all these things, we're going to have lots of people, and that isn't going to be an issue. So we want to find all the studies that we can to put into the meta-analysis, including the little ones with the big effects that are not significant and the big ones with little effects that are significant. We want all of the studies to go into our meta-analysis. Okay, so I hope that addressed the questions about so we will get to the significance of the effect size D. Whoops. But hold off on that, and we'll if you have more questions about the significance of the individual study versus the meta-analysis, then I'll come back and address that again. Okay, so here's the common objectives again. We want to show and interpret the distribution, find the mean, the variance, explain the variance, and look for problems. So we're going to start by showing and interpreting the distribution. So these are the D values, and this is called a forest plot. And this is a common representation of the data in a meta-analysis. So we started with Crawford, was study number 1. The effect size is 1.15. That little box here, the square, is at 1.15 on the outcome scale. And the confidence interval for that effect size goes from 0.28 to 2.02. And that's the wings here. So from 0.28 down here to 2.02 here. So each study is represented by a box, and the box gets larger as we've got a better idea about where it is because there's more people. So more people, they're heavier, the box gets bigger, the wings get drawn in. So we had 100, we had 8 and 20 people or something like that here. Here we had like 180 in each. So we've got a bigger box and the smaller wings because the confidence interval is smaller. So we're pretty sure, because we've got lots of people, we're pretty sure that the effect size is right around in here for this one. Because we had a small number of people in the first study, we're not so sure about where it is, and so the wings are wider. So every study in our 17 is represented here. And our overall estimate, combining all these, is 1.11. So there's right in the middle, 1.11. That's our best guess. That's our estimate of the grand mean over all the studies. And the confidence interval for that is 0.68 to 1.53. And that's the ends of the diamond here. I'm going to talk about how we get that estimate more in a second. But first, I want to talk about the displays. So there's a lot of information in this kind of graph. So you can see not only where the studies fall, but how precise the studies are, and you can see the overall summary. Okay, so that's a forest plot, and I like to sort the data by the effect size. So you can see that the smallest effect size was minus 0.06 here. I've made a mistake. This says Crawford, but it's actually not. So let's go find out which one it is. Okay, that's Davidson and Eden B. So when I told the computer to write this graph, I forgot to tell it to update the list of authors. So when we get to the actual code, I'll show you how to fix this. But so pretend for now that the list is correct here. This is correct. You can see that we go from a minimum of minus 0.06 to a maximum of 3.07. What you'd like to see is a nice gradual change from low to high, like this one. This one is from a medical study. It doesn't really matter of what it is. What I would like you to see is that you've got this nice gradual increase in the size of the effects. Here you've got sort of a jump from right around 0 to something larger, and then you've also got this jump up here. So if I were the one running this meta-analysis, I'd be going, what's going on here? Look at that. These are zeros. So there's some studies where there's no Pygmalion effect, and then there's some studies up here where there's a really, really big, 3 standard deviations is a huge effect size. What's going on here? So I'd be going back to my studies, my raw data, and rereading the authors and going, now why does this look like this? I wonder. Okay, so this is the sorted forest plot. I like these. I try to present these when I publish. Sometimes the publication requires that we do it like this or alphabetically or something like that. So you can do it. You can have the computer sort it whatever they require. But I like this because it's easy to understand what's going on, and you can see if the result is the way it's supposed to be. Okay, there's a forest plot. Then the other plot is the funnel plot. And so let me explain what the funnel plot is. So this is the 1.11, which is the mean, the grand mean overall across all the studies. This funnel is going from no standard error to a large standard error, which is the precision of the individual studies. So if all the studies are drawn from the population where the mean is this, we would expect to see these dots, and each dot represents one study, should fall inside this, the unshaded area. We would not expect to see these guys way out here. These are the ones that were around 0 in the forest plot. And here's that one that's 3, that's way outside. We do expect to see more variability down here at the bottom because the sampling error is greater. As we go up, we expect them to cluster really close to this center line because the standard error is smaller and smaller. Sampling variance is smaller for large studies. So the big studies are up here, the little studies are here, and we expect this to see the stuff inside the funnel. Here you can see we have lots of dots outside the funnel, and that means that there's a lot of variability or heterogeneity in the studies themselves. So it's a valuable diagnostic when you're doing this kind of when you're doing a meta-analysis. Okay, so there's the displays, the graphs for the meta-analysis. So that's the first part of the meta-analysis is done. So now we've done that. We've seen our data. I would worry about whether these guys are really in the same distribution as these guys. And so I'd go back and look. You want to make sure when you're doing this, you didn't make an error in coding. So sometimes these things are really big or really small because you made a mistake. So you got to go check that out. All right. So now let's assume that the data are all fine. We've gone through and we've double checked, even though the data are really, in our case, they go from -0.06 to 3, which is a really big range. We think we've checked it out. We're pretty sure that they're right. So now we're going to run the meta-analysis to find the mean or overall effect size. And what meta-analysis does is to take a weighted average. So the basic idea is the larger studies with more people get more weight in the overall mean. So with studies with hundreds of people, that's going to have a significant, a bigger impact on that overall mean than a study with 10, 20, 30 people. And this is just an illustration. If we had 3 studies and we had effect sizes like this, and we weighted them differently, then our weighted mean would, in this case, would be 0.48 if I did my arithmetic correctly. And if we didn't weight them, then we'd get a 0.6. And the reason is because the big study is the one with the small effect size. Okay, so that's what's going to happen when we do our meta-analysis. And what actually happens in this, in the kind of meta-analysis that I'm showing you, is that the weights are based on the inverse of the variance of the study. So for the correlation coefficient, it's going to be n-3 is going to be the weight because the variance is 1 over n-3. So with inverse variance means you just dump it upside down. And whoops, I'm touching my mouse and it's doing terrible things. Okay, so and the weight for the D statistic, since that's what we've got in this case, we've got D, the variance of that is computed like this, and then the weight will be 1 over this. Okay, find the mean. Okay, so we're going to use inverse variance weights, and now here's the data for McNatt. So this is the graph, the forest plot, and I'm going to skip over this part of it right now. So, but in the file that I gave to you, if you run it, you'll get these results for the meta-analysis. So estimate here, 1.1086, that's the mean, that's the grand mean. And here it's rounded to 1.11. This is the standard error. So this is how precise the estimate of the mean is. So a standard error is 0.22. If we take the estimate and divide by the standard error, we get a z-value of 5.1, which is a really big value of z. We get a p-value of 0.001, which is essentially 0. And now this is this p-value. That is the test for the significance of this. So is it believable that we would get a mean of 1.11 if the truth is there's nothing going on, that the population value is 0? Well, no, that's not believable. The p-value is, basically 0. The confidence interval for this estimate of 1.11 goes from 0.68 to 1.53. So that's the ends of this diamond here. Okay, so that's the estimate of the mean that comes from the CMA, not CMA, the Metafor package. I'm going to talk about this stuff more. I'm going to talk about this stuff more when we get to the next step, when we talk about heterogeneity and the variance of the thing. But first, I wanted to show you the mean. So we've got the graph, and now here's the estimated mean of these things. And for those of you who are interested in the significance, so if the confidence interval for each of these things contains 0, then it's not significant. So here we've got -30 to 0.18. So this one is not significantly different from 0. And these guys where the wings don't cross the 0 mark, they are significantly different in the individual studies. For the overall, we've got this diamond here, and you can see the ends of the diamond don't cross 0. And that is exactly what you're seeing here in this estimate. It's that 1.11 and the standard error and the confidence, the lower bound and upper bound are the ends of the diamond here. Okay, so that's the significance test for the overall effect in the meta-analysis. So we would conclude on the basis of what we know so far that the mean effect for the Pygmalion studies in organizations, that mean is significantly different from 0, and it's large. So it's 1.11 on average. Okay, so we found the mean. Now we want to find the variance. And in order to talk about that, I have to back up a little bit and talk about fixed and random effects in meta-analysis. So if we have all the conditions of interest in our meta-analysis, it's considered fixed. So if we have 2 countries that we're interested in, we've got Peru and Venezuela, and they're the only ones that we're interested in, and we've got the studies from those 2 countries, then we could call it a fixed analysis. In a random effects model, we've got a sample of interest. So we're interested in all the countries in the world, but we've only got studies from 10 countries. So those 10 countries are a sample of 100 or 200 countries, however many there are. Whenever we have a sample of countries or organizations or things that we have a larger population, then it's a random. Both of these, and they're different models, okay? So we need to know fixed or random because we're going to do a different data analysis depending on whether it's fixed or random. Both of them will attribute some of the observed variance to sampling error. So we know if we were to do the same study over and over again in the same place, we wouldn't get exactly the same results because the people would be different in our studies. If we account for sampling error, so if we subtract out the sampling error and maybe variance due to other sources, what's left over, this residual, is called the random effects variance. And I'm going to talk about the REVC, or random effects variance component. So that's the random, if it's a random model and there's variance left over after sampling error, then we're going to have a random effects variance component. Different people call this thing different. They call it different things, and they have different notation. So the Hedges camp, which is where Metafor came from, they call it tau squared. And you'll see in the output, the way they say tau squared in the output is tau hat 2. So that hat 2 means to the second power or squared. So that's the way they write it. Hunter and Schmidt talk about SD rho, and that would be written like this, SD sub rho. And that's the square root of tau squared. So if you have tau, that's what Schmidt and Hunter call SD rho. So there are different ways of saying the same thing. Different literatures talk about it in different ways. They all refer to the variability of the residual. And in Hedges, they call that heterogeneity. All right. So what you should know is that random effects models are the ones that have sort of won the day. You almost never see fixed effects models anymore. So I'm going to show you random effects models in the data analysis, and that's what you should be using. In management, you're always going to have organizations being sampled, or departments, or companies, or time points over time, or something that's a sample of some larger group that you want to know about. And so those things will be, it'll be a random effect. Okay, so this is an illustration of, a picture to try and get the idea of random effects again. So let's suppose we have 10 studies, and let's just look at this one first. This could be Pygmalion in some recruiting class in the Army in the United States, and if we did the study in that recruiting class over and over again with different people, we'd expect to get a distribution of the result. So we'd get a mean difference that looks like this. On average, it's right here, and most of the time it would be pretty close, but sometimes it'd be pretty far away. If we did a Pygmalion study in the Navy, we might get a result like this. If we did it in the Air Force, we might get a result like this. The idea is that this is the population, the larger population, and that there's some true underlying value of mu for each of these in this larger population. But when we go to do the studies, there's some uncertainty due to sampling error in each of the studies. So really, when we're doing a meta-analysis, there are two sources of uncertainty. There's uncertainty due to the specific sample of people in any given study. That is uncertainty due to sampling error of the ordinary kind. And then we have uncertainty due to the location of the underlying value in some larger population of studies. So the military studies, we've got the different branches, we've got the different kinds of services. We've got artillery, we've got police, we've got people who do the cooking and cleaning. We've got all these different things, right? So we've got two sources of uncertainty, and both of those things get considered in a meta-analysis. If you've been taught hierarchical linear models, then this would be like at the primary level, and this would be one level up. Okay, McNatt. So we've got 17 studies. In each of those studies, it goes from -06 to about 3 here. Each of those studies, if we did them over again in that same context, we wouldn't get exactly the same result. We'd get a distribution of results that would look like these things do. If we could do them over and over again, and we took the means of those things, then we'd get this series of results like this. And those things, the variability of this distribution would be the heterogeneity. The distribution of this stuff would be the overall variability. So we're going to take this overall variability, and the part that's due to within study variability, we're going to subtract out to get this variability. So that's what's going to happen when we're doing our random effects meta-analysis. So this is a recap of what I just said in a different way. So here we've got in a fixed effects, we've got one hypothesized underlying effect. It's the same, exactly the same for every study. But when we actually do the studies, because of sampling error, we don't get exactly the same result. And if we could do them over and over and over again, we'd get exactly the same result on average, and that would give us one estimate of the mean effect overall. So if we were looking at something like color discrimination for people who are not colorblind, if we go across countries or cultures or whatever, color discrimination is the same wherever you go in the world, as long as you're talking about human beings. So you'd get the same results over and over if you just had big sample sizes. On the other hand, for random effects, the underlying effect is a little different depending on where you are. So if you could subtract out the sampling error for each one and just look at the variability of the circles, you'd get this distribution here. This is what's left over. This is the heterogeneity. This is the random effects variance component. So if we take the total variability and we subtract out sampling error or sampling variability, we get this residual that is the variability of the true differences in the effects. So if we're doing studies about political views, or if we're doing studies about judgments of almost anything, then when we go from setting to setting, we see big differences in how people have values or views or opinions of things. So if we were looking at the effect of mindfulness meditation on well-being in different countries, we would see that the effects are different to some degree depending on where we go. Okay, so that's the idea in the random effects meta-analysis. So now, having said that, we're ready to talk about the variance for the McNatt studies. So here we go again. These are the studies. Here's the mean, and here's the confidence interval for the mean. Random effects model, it says K is 17, so we have 17 studies that went into the estimation. Tau square, so this is the tau hat 2 is their random effects variance notation. Their estimator is REML, that stands for restricted maximum likelihood. And this is the method that statisticians like, so that's what I'm showing you. There are many different methods that you can use. And if you go into the Metafor, syntax, it'll tell you, yeah, you can try various, you've got maximum likelihood, you've got Dursimonian layer, there's a bunch of estimators, but this is the one that the author of the program likes the best, so I'm showing you this one. I think it's really good. So here's tau square, estimated amount of total heterogeneity in this set of studies is 0.6727. Okay, so that is the estimated variance of this distribution. That's the estimated variance of this thing. Okay, the standard error for that estimate is this 0.28. The square root, so this is tau. This would be the same as SD rho in the Schmidt and Hunter approach, is 0.82. And I square is total heterogeneity, so that's the random effects variance component over total variability. That's the raw variance is about 95%. So this means that most of the variability that you see among these effect sizes can be attributed to true differences in the studies. And that's an important thing to know when you're doing a meta-analysis. So what you want to know is, does the true effect vary a lot? And in this case, the true effect of the Pygmalion, experiment varies a lot. So you got some studies that's down around 0 and some studies all the way up to 3. Okay, so there's a lot of true variability above and beyond sampling error in these studies. So we've got here's the estimate. Here's the square root of that estimate. Here's the test for heterogeneity. So this is the test for this value being 0. So is 0.67 a believable value if the truth is 0? And we find that the Q or chi-square statistic is 225. P-value is less than 0.001. So no, we can say that this is significant. So 0 is not a believable value for this. Okay. All right. So now I've showed you the mean, and I've showed you the variance or the heterogeneity. So this is the variability of the true studies. And I'm going to pause here and ask you if you have questions at this point.
Yes, there are a couple of questions which have been coming in. One of the participants, Kunjal Mehta, he has asked the question, is meta-analysis only for true experimental studies? That's the first question. Does structural equation modeling have meta-analysis also or not? That's what his question.
Okay, so the first question is is this just for experimental studies? And the answer is no. It's also for non-experimental studies with groups, and it's also for correlational studies. So in management, most of the studies are based on the correlation coefficient R. So it doesn't have to be an experiment. The kind of inference that you can draw is different for experimental studies and correlational studies, as I'm sure you know from your graduate studies. But the data analysis part is very similar either way. If we have time at the end, I have a data set based on correlations, and I'll show you what that would look like. Now, what can I have the second half of the question again, please?
Yes, he is asking, does SEM models have meta-analysis? That means, can we conduct meta-analysis for SEM models also?
Yes, and your instructor is going to talk about, at least I think you are, talk about how you do that. This is an active literature right now. So the best way to do structural equation modeling with meta-analysis is still controversial. But the idea, what people do is they do a meta-analysis for each element of a correlation matrix. So you've got, some kind of a leadership measure, and you look at productivity, and you look at intention to quit, and you look at leader member exchange kind of from the supervisor and from the subordinate, and you create a correlation matrix of these things, each of which is based on some number of studies, and then you input that into your structural equation program. I'm not going to show you that today. It is possible.
Okay. Now the next question is, do skewness and kurtosis affect the interpretation of effect size results?
That's a good question. So pragmatically, the answer is no. The assumption of these models is that you've got these nice normal distributions going on here, and you notice that now in defense of that position, you're talking about an effect size, which is a summary statistic. So as the sample size increases, those distributions should be normal or approximately normal, regardless of the parent population. Okay, so the theory is we're going to call it all normal, and we're not going to bother with kurtosis and all that nasty stuff, skew. If your effect sizes, you don't have very many of them, and you've got outliers, you're still going to have the customary difficulties in data analysis. But so far as I know, we just, in practice, we pretty much just ignore that. Sorry. If you can devise an algorithm that takes those things into account, you can make some money.
Right, so thank you.
Other questions? Okay.
Yes, sir. There is one more question, which the question is, the requirement of underlying data from various studies have to be parametric, non-parametric, or mixed?
Oh, so it should be parametric. So when you compute D or R, the assumption is that your data your data have intervals that are meaningful, so that when you subtract things, that that difference has meaning. There is a certain amount of controversy about whether most psychological scales have that property or not. My opinion, so, and this is just my opinion, different people have don't agree, but my opinion is that even though the psychological scales like leader member exchange or intention to quit or things like that, it's my opinion that it's reasonable to treat those as parametric, even if the intervals aren't exactly equal, or even though the intervals aren't exactly equal, because doing so tends to yield meaningful results. So if we act as if we had interval or parametric data, then our experience has been good, has been that the results are reasonable, even though the actual definition probably has been violated. So in theory, you've got to have the parametric data, but in practice, you can relax that somewhat, I think, and still get meaningful results. So when you go and look at the meta-analyses that are published in management, you'll see that many of them have these, use surveys.
Right, sir. Now, the next question is, what will be the null hypothesis, H null, for the test for heterogeneity?
The null hypothesis is that tau square equals 0 in the population. So right. So here is the estimate, and the null hypothesis is that tau square is 0.
Right, sir. Now, the next question is, how to interpret the results of meta-analysis given the different methods that are being used?
Okay, so the main interpretation should not vary depending on the method. So I'm not sure what you mean necessarily. Like if I change this from REML to DL or ML or something like that, my interpretation of heterogeneity and mean and the significance tests and their interpretation won't change. I mean, in this case, I would say, the mean here is large and significant. And that would be the case regardless of which method I used. And I would say that the heterogeneity is large and significant in these studies, and that wouldn't change regardless of the method. Maybe the person who's asking the question means something different by method than what I'm thinking, but I'm thinking, I'm showing you one program to do this, but it won't matter much whether you use the Psych Meta or you use CMA or you use a Metafor. All these different programs will give you analogous results. So they're all going to give you the overall mean. They're all going to give you an estimate of the heterogeneity. They're going to give you, that people will show funnel plots and forest plots and things like that, and those will be sort of universal. So did that answer the question or no?
I think that answers the question, sir. Now,
Okay.
as we have decided, maybe we can take, yes, she has thanked you and saying that was the answer that she was looking for. So she is satisfied, sir. Thank you, sir. So should we take a break now for, you want 10 minutes break?
Yeah, that's okay. That sounds good to me.
So, right now it is 3 minutes still left for 9 o'clock, so that's fine. We will resume again by 9:10. So after 10 minutes. Okay.
Great.
Thank you, sir. Thanks a lot, sir.
Thank you. So we're taking a break.
Are you?
Yeah.
We're going to the drugstore and the grocery store.
Okay.
How's it going?
No, teaching on the web. It's just quiet. You can't see them.
Yeah.
You can't hear them. I think it's okay. They are asking questions.
Good.
So that's a good thing.
Good. Good.
I'm not hearing a bong. So and so has left. That's just. She said the attendance is mandatory. So.
Thank you, sir. It is really good to learn from you.
Thank you. Very nice of you to say so.
Yes, sir. I mean, I'm seeing right now certain things are there which you are making it absolutely clear.
Hope so. I hope, yeah. So one of the great things about being a teacher is sharing things that you know with other people, and it's very rewarding to maybe. I mean, I'm hoping that that your class will go on to do meta-analyses and publish them and become rich and famous and do all the all the successful things that you can do.
Yes, sir. We are going to invite you once again. This is not the first and last. So more in-depth study and learning also is also there, sir, for us.
So are we back?
No, sir. I think we still have some
Okay.
time.
Okay.
So,
All right. So just let me know when the time is. So
yes.
you're a philosopher by training, is that right?
Yes, sir.
Okay. And what would you? So I've known a few philosophers. In what tradition does meta-analysis fall? Like, is it logical positivism or what do you? I mean, it's empiricist, but
Yes,
how would you describe it?
It falls under positivism, number one, and further there are around 12 schools are there, sir, for positivism. So it again comes ahead for logical positivist.
Okay. 12.
So yes, so there are a lot of things that they are talking about, especially as you are discussing about the population, how each and the text that you're talking about, and especially when you are comparing them with the entire thing or the variance which is there. I mean, these are the things that the statistically the realities are, right, in terms of the numbers.
Yeah.
Now, positivists are more interested to interpret these numbers and try to understand that, yes, see, this is my reality. Now, for example, when we go ahead further, and I learned about meta-analysis, they told me that apart from these numbers, we are also looking at publication bias.
Yeah.
Then a statistical biasness. Now that is where I'm stuck up with, and I am looking forward to read or learn more from here and try to understand from the logical positivist point of view. Okay, these numbers are there. However, as you are pointing it out, that yes, this is going to fall here, the way the cube or the square is increasing or decreasing. You see, behind that also, there must be other calculations which are present. And that was number one. And I'm right now focusing on these things, basically. So the entire meta-analysis falls under the logical positivism. So that is the
Okay. Yeah. The whole publication bias and the bias in the meta-analysis is a serious concern, and it's an area of active research now in the methodology of meta-analysis. So people are really interested in using the data that come from a meta-analysis to try to determine if there's bias, and if so, how much, and if so, whether the data can be used to correct that bias to result in an estimate that is more accurate. So I'm going to show at the end one of the ways that people are doing that. But it's a thorny issue. So yeah, we want to know what the reality is, but the numbers can be misleading if especially if there's somebody who's trying to make it misleading to begin with.
Yes, sir. That's right. So that's where I'm stuck up with, and now I'm trying to understand, the depth of it in order to see how these numbers, should we go ahead and take the support from Plato, because he
Yeah.
talks a lot about abstract concepts and the entire mathematical realm, philosophical. If I look at the philosophy of mathematics completely,
Yeah.
Russell, Whitehead, Moore, they all are the ones who were discussing and they gave importance. So on one hand, we have the statistical tools. On the other hand, we have those, thinkers who are giving a lot of importance to the numbers. And then coming towards the qualitative schools, they say that forget about that. Now look at, try to understand and proceed further. So you see, the
Yeah.
dilemma between all the three are present for us. So somehow we need to, bridge in,
Yeah.
link in something. So
Yeah. 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 That's life.
yes, sir.
Yeah.
Sir, we can start off now, sir.
Okay. Welcome back. We've talked so far about the mean, the variance, and the display of the results. I want to continue a little bit with the variance, and so you probably are familiar with the idea of the confidence interval, but there's an additional interval that's important in meta-analysis called the prediction interval, and the Schmidt and Hunter call it the credibility interval. They're computed a little bit differently, but they're referring to the same underlying phenomenon. So in the McNatt data, the value of the mean and what you'd guess on average is 1.11. The confidence interval for the mean was from 68 to 1.53. So if this were 1.11, then the confidence interval would be right around here, 0.68 to 1.53. And now the prediction interval here, it's written CR.LB, for credibility, lower and upper. They've got -55 and 2.77. So this actually refers to an interval in the underlying distribution, the distribution of the true effects, where we're talking about a lower bound, like 95% or 95% is in the middle. We've got 2.5% down here and 2.5% up here. These boundaries, -55 and 2.77, would be the edges of the center or the middle of the distribution. Let me say this a different way. If you were able to go out and find a Pygmalion study, and if you could see through the sampling error to find the true value, the mean value for that study in that context, then 95% of the time, that value would be between -55 and 2.77. The interpretation of that is the mean is high, and we're confident that the mean is high. However, there's a lot of variability in the true value underlying the Pygmalion effect, and it could be very small or possibly even negative, and it could be very large. So we don't really know if you're going to try a new Pygmalion study. We don't really know if you're going to get a big value or a little value. If it had been the case that this value, the random effects variance, was 0 or close to 0, then this confidence interval and this credibility value would be the same, because all the estimates would be right around the middle of the distribution. This thing would be shrunk to a point where we're talking about there's no variability here. They're all the same. And so all we have to worry about is how well we've estimated the mean. All the values are the same. Where there's a lot of variability, then this spread is quite wide. And in the case of the Pygmalion effect, that's the case. So It's very, very widespread. So the average effect for McNatt is large and positive, but that effect could be small or even negative in some contexts. So that's what I would tell my reader if I were writing this up for publication. My interpretation of the things that we know so far about McNatt is we have 17 studies. Based on those 17 studies, the typical or average Pygmalion effect across the population of studies is large, it's positive, it's significant. On the other hand, there's a lot of variability underneath beyond sampling error that's due to differences in the studies, such that some of them are probably large and some of the effects are probably small or possibly even negative. Okay, so now we've got the distribution, we found the mean, we found the variance. The variance is big. We'd like to be able to explain that more than just, well, it's sampling error. So what we typically do in order to explain the variability that remains after we take the mean is to look for what's called moderators. So part of the variance is due to sampling error, but there's usually stuff that's left over. And in the McNatt case, there's a lot left over. So we're hoping that if we did our upfront work properly, we've collected some data that might explain the difference among these studies. So a moderator is some variable that might explain that residual variance across the studies. And the idea of a moderator is it's a third variable that conditions the relations between the two shown in the effect size. So in the effect size in the McNatt data, the relationship is between performance, job performance, and group membership. So are they in the Pygmalion group or are they in the control group? So do we have something that will explain that association? For a different example, if we take SAT scores and we predict math grades from them in college, so we've got SATQ, the quantitative part of the Scholastic Aptitude Test. We can correlate that with grades in math classes in college. And it turns out that the correlation for females is larger than the correlation for males. So in that case, sex, male versus female, is a moderator of the relations between the SAT scores and the grades. What we want to find in our McNatt study is something that explains the difference in the size of the Pygmalion effect. We can have moderators that are either categorical. So that's analogous to factors in analysis of variance. So country or study type, like published versus not, or dissertation versus not, these can be analyzed by an analog to analysis of variance in a meta-analysis program. And then we have continuous, moderators. So time between tested and retests, so the age of participants, the size of the organization, the date of publication, all these continuous variables that might explain differences in the effect sizes. Those things are analyzed by weighted regression, sometimes called meta-regression. So in McNatt data, we happen to have a moderator called organization type. You might remember we had military and civilian organizations. So we're going to code for that. We're going to test, to see whether there's a difference between the military and the civilian organizations in the overall effect size. So the way that you run this in this particular program, I'm going to have a result called a result 3 or res 3. RMA is an R meta-analysis. So that's what you say to call up Metafor. Data is McNatt. That's the name of the data set that I showed you in the beginning of the lecture. My dependent variable, y sub I, is equal to the values of d. So that's our standardized mean difference. The variances, the sampling variances come from a column that I called V in the data set that I showed you. And now mods for moderators equals, and then there's a squiggle for is distributed as org. So org is the name of the column that has military versus civilian in it. So this is how you tell the computer to run the moderator analysis. And it comes back and it says, I've still got 17 studies. I'm still using restricted maximum likelihood to estimate. We've got the same set of estimators. So we got tau square and tau, and we've got I squared and A squared. And now we've got R squared, which is the amount of heterogeneity that's accounted for. What that means is how much of that residual variance, the random effects variance component, that residual variability or heterogeneity, how much of that was accounted for by organization type, military versus civilian. And unfortunately, it says 0%. The test for residual heterogeneity, so that's this stuff, what's left over, is still nice and big and significant. And the test for the moderator, so this is the test of, here it says coefficient 2. And what that means is the test of differences by organization type. So is there a difference in effect size by military versus civilian? And you can see that this is a not significant difference. So it tells there's no difference here, and it's not accounting for any of the variance here. And the result here is where it says intercept is 1.07. And so that is the mean of the civilian samples, and the mean of the military, so it has M here, the military samples, the mean of that is 0.6 higher than this. So you've got 0.6 and then 12 here, and basically the overall result was like 1.11 or 1.11. Okay, so this is the test for the difference here. The estimate is a difference of 0.6, standard error, z-value, you can see it's not, unfortunately, not a very big value. The p-value is the same as, where did we see this? Here, p-value is the same as that. So this test here, it's not significant. The confidence interval for the size of the difference goes from -87 to 1.03. So we can't reject 0 as the value for the difference of the means. Okay, so this is how you would test for a moderator effect. You can put in continuous variables or categorical variables here, and the RMA will analyze by this meta-regression or analog to analysis of variance. You can have more than one of these in here. I should tell you that it's hard to get a model that has many independent variables. So in your research, you may be used to seeing models, regression models that have lots of independent variables and all kinds of control variables, and you might have 10 different variables in there. What happens in meta-analysis is that you begin to have terrible missing data problems. So in this case, all 17 studies, we could tell if they're military or civilian. But oftentimes, authors do not report things that you want to know. So what branch of the military? Well, they might not have said that in the military studies. Or how many people were potential recruits? Well, we don't know that. So, or we know it for some of the studies, but not for others. So by the time you get several different moderators in the analysis, you wind up, if they're missing and you kick out missing for anything, then you wind up with basically no data left to analyze. So most of the time people will analyze these things one at a time, even though from a regression standpoint, that's not the best thing to do. Okay, so this is how we would analyze for org type for the McNatt data, and this is an attempt to explain the variability of the effect sizes. In this case, the attempt failed. I'm going to show you org type one more time, and this time it says mods are distributed as org -1. So the only difference here is I've got a -1 after the org. This is going to give you a different test, and you need to be careful about which one you do because it's easy to make a mistake and misinterpret what you've got. So here you can see the test of the moderators, coefficients 1:2, is significant. So what this means is that the average of these things is not 0. Okay, it doesn't mean that there's a difference in civilian versus military. That means that the average civilian and military estimates are significantly different from 0. So it's not a test of the moderator, it's a test of the effects. Okay, so here, if I do it this way, I get separate estimates for the civilians, 1.06, and the military, 1.1305. Okay, and they're both significant, but they're not different from one another, and we found that out in the previous. So here's the test of the difference, and that tells you whether there's a difference by org type. Here it is the estimate for each of the org types. So you might want to know each of these things, and you might use this program to get this information. But you need to be careful about what you're asking for and watching what you get for the results. Otherwise, you could misreport this in your publication, and that's extremely embarrassing when somebody points out that you made a mistake in your publication. You really want to avoid that if you can. Okay, so there's the results for the moderators. Okay, so now we have shown the distribution. We found the mean, we found the variance, we tried to explain the variance, and now we're going to look for some problems so that there's an old saying, garbage in, garbage out. So meta-analyses tend to be very influential and very persuasive because you get all these studies and you say, okay, here's the result from all these studies, and your individual study isn't nearly as weighty as the mean of 15, 20, 30 studies. But if the studies that went into your meta-analysis are biased or somehow they're bad, then your overall result is going to be biased or bad. So we want to look for problems in the data and see if we can't sort that out before we tell people here's the result. Or we want to show people the full. What I recommend is that you show people all of the data so that you're by analogy, your cards are on the table. You show people, here's all the data, then here's a problem that I found, and here's what happens when I correct the problem. And here's what I believe the best result to be, but you can see here it is before and after, and the reader can make up his or her own mind. Okay, so the problem of bias is more generally problem of availability. So we can only meta-analyze what we can find. And if the studies that we can't find are missing at random, then our inferences will still be good. So if the model is good, the model is a reasonable representation of the data, and we're missing some studies, that's okay, especially if we have lots of studies, because we're going to get the same result on average no matter what. But if the studies that we have in the meta-analysis are non-randomly selected, so there's an availability issue, now we have potentially a biased meta-analysis, and we have to start worrying. And unfortunately, there's lots there's lots of potential problems. There's lots of reasons to believe that our study sample might not be representative. One is publication bias. So that happens because if the study is small, then the effect size has to be quite large before the significance level is reached. So it's harder to publish. It's not impossible, but it's harder to publish studies that have a non-significant result. And people who do studies, researchers, know this. And so if you're doing your study and you come up and you get a null result, you may just decide to stop working on it then because there's only so many hours in the day, and your tenure depends on getting lots of studies published. And if you think this study is not going to get published, or it's going to take an incredible amount of time and effort to get it published, then you may spend your time doing something else. And if that's the case, then that study doesn't appear in the in the literature. And then the person who goes to meta-analyze can't find it. English there's more stuff published in English than in other languages. And if you only speak English, now I realize in the great audience that I have today, this is not the case that you speak English and other languages, but here at home, it's often the case that people only speak English and not other languages. And so if it's published in some other language, we can't read it. And so it doesn't appear in our meta-analysis unless we have somebody on the team who speaks that language. If you belong to certain kinds of societies and you send an email out saying, hey, anybody done a study on X, Y, or Z, then your friends may send you studies. And so it's a non-random sample of things. You're more familiar with stuff in your own field. You can probably find things that are difficult to find and include in your study. You're not supposed to publish the same study in more than one place, but people do. So there's, as I alluded to earlier, there's this terrible pressure to publish for tenure. And so people are motivated to get the most number of publications they can. And sometimes we'll do some iffy things, some things they should not do in order to increase their publication rates. The significant studies are more likely to be cited and thus easier to find. Dissertation and other file drawer problems, where people just decided not to write the thing up for publication, those are hard to find. The worst thing, the thing that really worries me, the rest of the things I've talked about so far are usually not too biasing. Publication bias is possible, but it doesn't worry me too much. Deliberate misrepresentation for financial reasons bothers me. So if we're doing studies of a drug, it's in the financial interest of the drug maker to have those studies come out a certain way. When people were doing studies of cancer and cigarettes, the tobacco producing companies paid for a lot of those studies. And it's in their financial interest to have the studies come out in a certain way. And so when there's good reason to believe that money is involved in the outcome of the study, then I am worried. I'm starting to get suspicious, and I would like some external agency to be involved in the data collection and representation if possible. Okay, so that's the reason to worry about it. So what we try to do in our meta-analysis is see if there's evidence of the bias and what effect does that have. So people have devised ways of looking at the data to see if there's bias and to try and fix that. One way that people have proposed is to create registries for studies. So if you register the study before you do it and then you post the data to that registry, no matter how it comes out, then by golly, it's not going to be a bias, that the registry won't be biased. We can look at the data that we get, which is what most people do because the registries haven't taken off yet, and see if we can find evidence for bias. And I'll show you one method for doing that in just a second. Unfortunately, it's hard to be conclusive about bias unless someone admits to fraud. So, all of these techniques that we've got now, and this is an area of literature that's growing. People are really working on it right now. Nobody's got a foolproof, looking glass kind of thing where you can actually see and know for sure what the deal is. Well, one thing that we can look at is asymmetry. So if there's no publication, if there is publication bias based on the typical P is less than 0.5, then we expect to see studies with significant effects in the data, but the non-significant ones will be missing. So if P is less than 0.5 is a barrier, then studies where we've got P is less than 0.5 will be missing either completely or some of them will be gone, but not all of them. And so what happens is that if you have a funnel plot like I showed you at the beginning, then studies on the left side will be missing because that's the side where they're non-significant on that part of the funnel. So in other words, we know in order to get a significant result, if you have a small sample size, you have to have a big effect size. So those studies that have small sample sizes will have big effect sizes if there's publication bias. Okay, so we can look for symmetry and asymmetry in the set of studies that we have. So this is a funnel plot, and it doesn't have the shaded portion like the one I showed you earlier, but we can pretend that the shaded portion is outside the triangle. And so what we expect to see is that if there's a common effect or single effect here with the open triangle, and the studies are all representative of that, then they should fall within the triangle, and you'll see that there's a symmetry in the way that they fall. So the funnel should be filled. And in this particular case, the funnel is missing a bunch of studies on the left side. And that is consistent with publication bias. So one analysis that looks at this pattern of results and tries to combat that is called trim and fill. And so what it does is it trims studies off the edges of the funnel until it achieves symmetry, and then it fills them back in on the left side so that there is symmetry. So you can see that these studies here on the right are mirrored here on the left. So it's trimmed the whole distribution until it found symmetry, and then it's filled, excuse me, on the left side here to make the distribution symmetrical. Then the entire analysis is recomputed, including these added studies. And when we do that, we get this black diamond. So now the mean effect size has moved down a little bit, and you can see that the edges are moved down as well. In this case, it looks like the revised estimate is still beyond 0. So you would have a positive effect in either case. But this is an attempt to first diagnose the asymmetry, which is an indication of publication bias, and then an attempt to rectify or remedy that by adding in the missing studies. So you need to keep in mind, if you do this, and it does change the result, that trim and fill is a sort of a sensitivity analysis, a sort of what if. What if there were bias, and what if a bunch of studies were missing, and what if that result were symmetrical? Well, if that's the case, then we would expect to get this new result. So if you're doing this, you want to present the complete picture. So you want to tell people, okay, here's before, here's after, and what you make of that. In this particular case, though, this is not the McNatt data, okay? This is a different example. In this particular case, I would say it appears that there may be publication bias. However, that publication bias, if present, would reduce the effect overall, but does not reduce it to the point where the null of 0 effect is plausible, and it's in this range, and then I would try and interpret whatever that range is for the effect in question. So is it still practically significant is what I would want to talk about. Okay, so for the McNatt data, the command is trim and fill, and it estimated the number of missing studies on the left side to be 0. So what it's saying is, I think the distribution of effect sizes we have is sufficiently symmetrical that it doesn't need to impute anything. And so the revised result is exactly the same as it was before. So it didn't impute any studies. And so it's telling us that it thinks that it doesn't see any publication bias for these data. Okay. All right. So that's the trim and fill result from McNatt. And just to reiterate, there's lots of different kinds of studies. This is an active area, and there's a lot of different approaches. And if I were going to do different approaches in any depth, then I'd have to spend a whole couple hours doing that. So I'm showing you one, and I'm trying to hit the highlights for the most important things that you do in a meta-analysis. So here's the conclusions that I would, that if it were me writing this as a meta-analysis for publication, I would say, we have, 17 studies that I collected in thus and such a way. And it's important to understand the Pygmalion effect because of blah, 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 blah. And, you have the whole introduction. And then in the results, I would say the overall mean was positive and significant. However, there's a large amount of residual variability such that some applications are positive, but others may be zero or not positive at all. I tried to find out whether organization type, military or civilian, could explain the differences, but apparently it did not. So organization type didn't explain this underlying variability. Based on the one test for bias that I had, I couldn't find any evidence of bias in these. My speculation that would go in the discussion section and not in the results would be that I think the Pygmalion effect only works if the target of the Pygmalion effect, the teacher, the instructor, the supervisor, doesn't know the people that are being prognosticated beforehand. So if the teacher has a new group of students and they're told these 3 guys are going to be bloomers, then it's probably going to work. But if the teacher is told halfway through the year, these 3 guys are going to be bloomers, they're likely to go, no, I know these people, and I don't think the test is right. I don't think anything's going to happen to them. That's speculation on my part. I don't know that for a fact. If I were doing this as a publication, I might go back and try to look at the individual studies to see whether I could tell if the Pygmalion effect was done with folks that already knew the recipients or not. But anyhow, that's what I would do for McNatt. Okay, so let me, so I want to give you a few caveats here, and then I would like to go show you the code. So actually run some code in R so that you can see it. I didn't talk about a lot of topics in meta-analysis that are active or important, but I thought these are the things that are really essential that you need to know in order to read a meta-analysis or in order to begin to do one yourself. I have lots of videos about Metafor on YouTube that you can look up. Lots of other people have videos on Metafor that you can watch. There's a ton of stuff. The difficulty is sorting out the wheat from the chaff, as it were, on YouTube, but there's a lot of good stuff out there. Fichtbauer, who's the guy who wrote the Metafor program, has a really good website that he works on all the time, so you can look him up. The citation for that, for his, not for his website, but for the program itself, is shown here: Conducting Meta-Analysis in R with a Metafor Package, Journal of Statistical Software in 2010. So if you're going to use Metafor, I would suggest that you read that. And for a really nice, accessible explanation of what meta-analysis is, this book by Borenstein et al., 2009, Introduction to Meta-Analysis, is really good. It's really clear and easy to understand. So those would be my notes. And I think we have time to quickly walk through the R code for the McNatt data in RStudio. And as I say, your instructor has experience with R and RStudio, so you have some people who can help you with that if I'm not around. Okay, so there's the lecture, and now I hit escape, and now I'm going to minimize that and call up R. Okay, so now is the print on this too small to read, or can you actually read it in your?
Yes, sir.
You can read it?
Little bit more, sir, so that it is visible.
Okay, so there's a way to do that, and I don't remember what it is. Global environment. Let's see. Oops. Uh-oh. Oops. That was a mistake. I'm not sure. Let's see. Oh, wait a minute. I have an idea. Let's try.
Sir,
You can go to the tool options. There's a global option. There you can increase the fonts. Tools. There's a tools on the R. There you can use global option. Then you increase the font.
I do not see tools.
You
sir,
need
you
to
can go to tools.
Aha! Tools. And now,
Global
global.
option.
And now, uh-oh, now I have a
Get
cat
the
who's
font
attacking me.
option.
Hold on. I'm just having to deal with my cat. And now I'm looking at what, appearance?
Appearance.
Yeah.
14 fonts you can use it, sir. 14 or more, whatever.
Try that.
Yes, apply.
Yeah. Okay.
Okay, sir. I think this is visible.
Okay.
Yeah.
Okay. So this is our studio has multiple windows, and our code is shown here for the source code. If there's a hashtag, R will ignore the things to the right of that. So all this stuff is just notes to me. If you're doing this for the first time, you got to install RStudio and R. And then if you're going to do Schmidt-Hunter, you want to install PsycMeta. And if you want to do Metafor, you need to install that. I've already installed it, so I don't need to do that. I do need to open the library for Metafor. So I hit that and I hit run, and it says library Metafor is a program, and now it's loading it. And I set this little greater than sign here, and that means it's not giving me an error. So I like that. And now I'm going to select and run the data set for McNat. So there's a little run button here. Click that. And now I have input the data in the syntax here. I don't do this for actually running a meta-analysis. I input the data in Excel and then import that. But I wanted it in here so that when I sent it to you, you could run it without having to import. So here I've listed the studies and the years and the sample sizes and the effect size and the organization and the variance. And here I've combined them into what's called a data frame. And here I'm called McNat, and here I ask for McNat. And this is what I showed you in one of the slides. So you got the author, the year, the sample sizes, the effect size, organization, military, civilian, and the sampling variance. And now I'm going to create something called McNat2, which is the same thing, except, doggone it. So when I touch my mouse, it moves run. So the order command sorts things. So I'll just see why in a second. Res1 is the garden variety meta-analysis, and you can see it's our meta-analysis, data is McNat, dependent variable is the effect size, sampling variance is V, and method is random restricted maximum likelihood. And I run that, and now I get, this is the random effects variance, the REML 17 studies. I'm sorry. I have a cat who's persistently trying to climb on my keyboard. I'm having to fend him off. Here's the estimate. It's 1.11, and the big Z value, and the P value is great, and all that. And here's tau. This is the results of the meta-analysis. So you got the heterogeneity, and you got the mean. All right. So now, close that again. What else did I want to do? All right, well, here's the same thing, except for it's based on the sorted data. Run that. And when I run that, I get exactly the same thing, which is what I should. I'm going to skip that for now because I didn't talk about it. Here's the predict. Run that. And here's the value you get. Here's the mean. And here's the confidence interval. And here's that credibility interval that I showed you. So that's how you get that. And then now that I've got videos on how you do the graphics. Graphics are annoying in in R, but they will get you where you want to go. So CMA, for example, has nicer commands for graphics, but they don't come out publication quality. This is really nice what it does. So I hit the run here, and so now I'm asking it for a plot, and the plot appears in the bottom right window, and I can hit the zoom button, and so that's interesting. It didn't do this before where it occupies my whole screen. And I hit, oh, that's interesting. So this is surprising me. Let's try that. So usually it doesn't do this to me, and I don't know why it is. Okay, so in my screen, this actually is a pretty good looking graph. I can also, so when I want to publish, I can save as image. I can, let me do this, save as image. All right, so now it will allow me to specify the height and width and the place to put it, and it'll save it as a JPEG or whatever I want, and then I can include that in my publication. So that's a really nice thing. So this is the graph, and I told you when I showed you the funnel, I mean the forest plot with a mistake in it, I would fix it. So these labels come from the McNat data, and I need the sorted data for the one that's sorted. So that's McNat 2. So if I run that, all right. So now Davidson and Eden, the small one is -06 is actually, it's not Crawford anymore. It's the proper one. So now they're sorted properly here. So it takes a little while to learn how to make these graphs the way you want them, but it's worth it. Here's the funnel plot. Here's the moderator analysis, and make that visible. So this is the one that for org M, that's the difference in the two groups. And then if I want to see separate analyses for the two groups, I can run it like this with the -1, and it'll tell me here's the estimate for the civilian, here's the estimate for the military. And last but not least, the bias analysis for trim and fill. It's got that it estimated 0 missing studies here, so it's sufficiently symmetrical. Okay, so that is I'll make it smaller. And how do I make it? Okay, it should You should be back to the original screen now. What questions have you got based on the entire presentation? We still have 7 minutes left. I'm feeling great.
Okay, good, sir. We all learned a lot of things out here. And I have a few more questions coming in, sir. We will take up those questions also out here. Now,
Yes,
the
please.
first question they have asked is, can we consider both the studies, correlations and mean together in meta-analysis?
Sometimes the effect sizes can be converted one to another. So let's say that we've got males coded as 1 and females coded as 2, and we're looking at sex differences in some value, like values about collaborative leadership. So some studies might report a correlation between sex and values, and some studies might report a mean difference between sexes on the values. The meta-analysis requires that all of the studies be in a common metric. So you could convert all of them to mean differences, or you could convert all of them to correlations. And there are formulas that let you do that. And then you could run the meta-analysis based on whatever it was, that common index. You can't have just like the mean of values for some studies and then a correlation or a mean difference for other studies. So the effect size has to be a common one across all the studies. Otherwise, you can't take an average.
Thank you, sir. Now, second question is, what estimates can be given for an effect size with less bias?
So I'm not sure I understand the question. So one response is that there are a bunch of different algorithms that are intended to correct the overall estimate for bias in the data. So the trim and fill is one, but there are many others. So there are several regression approaches. There are some approaches that are based on p-values. So there's a whole bunch of them. And like I say, this is an active literature right now. So if you go into the methodology of meta-analysis and you start looking for correcting for bias, there are lots of different methods. So if you just, I'm sure there are even review papers on this now. So if you just Google that, you can find lots of different methods. Now that's only one interpretation of that question. If you mean correcting the effect size itself, that's hard to do. Given meta-analysis is typically based on other people's work, so you get the publication, and you get the dissertation or whatever it is. You've got an effect size that you pull directly from their paper. You don't get to compute it, so you can't really. Well, I'm sure you can, but it's not obvious how you would go about correcting the specific effect size for bias. It might be possible, so certain studies are like probability sampling studies for people's opinions about things, and they use those probabilities to adjust the estimate for depending on what you consider the population to be. And so those kinds of things are possible, but generally not possible for the meta-analyst who's just got to sort of live with whatever effect sizes they've got. I hope that addressed the question.
Yes, sir. Thank you, sir. Now, one more question has come in. They're asking for the link to watch your videos on YouTube.
So I think, I've got, all right, I'm going to call up, all right, I'm gonna try Google, no, not Goggle, Google, and let's see what happens when I go Google. And I'm going to go to, oops. Oh, I don't want the browser. I want Google. Okay, so now I want, I want YouTube is what I want. YouTube. All right, so I go to YouTube, and now I'm click YouTube, and now I'm going to search Michael T. Brannick. Let's see, I want Meta. Now, let's see what happens if I do that. Okay, so if you go into YouTube and you type Michael T. Brannick meta-analysis, then first thing that comes up is Introduction to Metafor for Meta-Analysis in R. So it looks like, oh, and you got Michael Borenstein. So if you want CMA, which is one of the easy, it looks like Excel. Then you've got him, and then for me, so instead of meta-analysis, type, let's see, Michael T. Brannick Metafor. Yeah, that's it. So if you type Michael T. Brannick Metafor, you'll see my videos and a bunch of others, but mine will be there. I don't have a URL that just grabs them. I guess I have a channel, but I don't remember how you find channels, and somebody knows how to do that in Google, in YouTube. That will work. What else?
Fine. Thank you, sir. I think that's the questions I have got.
Okay.
One last question from my side, sir. What is the difference between using the packages MetaSem and Metafor? Because you see, both the packages are being used for meta-analysis, right?
Yeah.
What is the advantage of using Metafor versus MetaSem?
MetaSem is meant for the SEM approach to meta-analysis. Metafor is not.
Okay.
So Metafor, I'm not that experienced with MetaSem because it's newer, but Metafor has a whole bunch of really nice things for doing meta-analysis. So the graphs and all that kind of stuff are in there. The diagnostics, for a garden variety meta-analysis, Metafor has everything you want. It doesn't, it wasn't meant for MetaSem. So if that's really what you're trying to do, then I would go to get MetaSem and use that. But if you're gonna do an ordinary meta-analysis, you won't need it.
Right, sir. Now, one more thing, sir, a quick group photograph for all of us. So I think all the participants can go ahead and, come to the video mode so that I can take the photographs very quickly. Can you all come over to the video mode? Thank you, Bharat sir, Atutosh sir, Kannan sir, and I will quickly take over the photographs. Thank you. If you can just hold on for a moment. Thank you. 1 second. Thank you, sir. Thanks a lot, all of you. I really appreciate it. And sir, thank you once again for such a lucid and wonderful lecture, I should say a session. It was indeed a master class in very simple terms, and in a very nice manner, we were able to understand what meta-analysis is all about. And in our especially, in just a few codes and with our script with us, I think each one of us would be able to go ahead and at least, try coming up with forest funnel or the other funnel that you have shown to us, the plot, and we can definitely go ahead and try a little bit on our studios also, sir, with Metafor package.
Great.
So I really appreciate you coming over here, giving us some of your valuable time, and we will meet again very soon, sir. I will get back to you again, maybe after February 15th, and we will discuss more about it. On behalf of the entire team of this particular workshop, thank you, sir. And I can see the tail of your pet. Yes, what is his or her name?
This is
Hi.
Clyde.
What?
This is
I love
Clyde.
animals. Okay, wonderful, sir. So she's also there for the photograph session. So we could see that one also. Thank you, sir. And
Thank you.
to you. I will send you the link for the particular video
Okay.
of this session also, sir.
Okay. Thanks, everybody. I
Thank you,
appreciate being
sir.
invited.
Thanks a lot. Namaste from India, sir. Thank you.
Bye.
Bye, sir. Bye-bye. Thank you, participants. I really enjoyed all of you. It was a typical family kind of an environment wherein all of you must have enjoyed learning little